So good morning and welcome to the school, which is part of the program on entropy, information and order in soft matter. So Chandan will say a few introductory words later on about the school. So the first lecturer for the day is Chandan Dasgupta.
Okay, thanks Pinaki, and good morning and welcome to all of you to this school. I have been asked to say a few things about the school as such. I mean, what are the topics, what is it that we are trying to do here? So I'll just take a couple of minutes to tell you about it. Of course, I mean, all this information is already available at the website, and who is speaking in which week and so on and so forth. All this information is already available to you. The basic idea, of course, is to have sort of somewhat extended school where we'll discuss various aspects of soft matter physics, which is, of course, as you all know, very popular all over the world, as well as in India. Many people are working in this area. And it's an interdisciplinary area where people from physics, chemistry, biology in particular, which has made this area very popular, various engineering disciplines like chemical engineering, also information science, people from all these various fields are involved. Of course, I mean, it's not possible to cover all aspects of soft matter physics in a school like this, so we sort of try to sort of zero in on a set of topics which will be sort of emphasized in this school. And there, the topics that we have chosen deal with basically the role of entropy in soft matter physics. And which is very important in the following sense, that in many cases in soft matter physics, the systems that we are dealing with are athermal, in the sense that the basic objects that sort of form the system are big, so thermal fluctuations are basically unimportant. And so basically entropy plays a very important role in determining the properties of such systems. And there are several topics related to entropy in soft matter that will be covered in this school. For example, entropic considerations in self-assembly. There will be Professor Sanat Kumar this week, whose lectures will deal with mainly this area. Next week there will be Francesco Sciortino, who will also talk about self-assembly, the role of entropy. The next week, almost all the lectures are going to be devoted to entropic considerations in glassy systems. Then there are, of course, as I just mentioned, there are many soft matter systems which are athermal in the sense that the usual ideas related to Gibbs ensembles and so on, equilibrium, statistical mechanics don't apply. So one has to sort of develop new ideas. In particular, for example, in granular matter, which again Bulbul will cover part of that this week. Also Sriram Ramaswamy. Then active matter, biological systems, all these things will be covered partly in this week and also in the last week of the school. Then there are entropic measures of structural patterns and order, which Professor Levin will be talking about this week. So there are these various topics which are all related to entropy in soft matter, which will be discussed in some detail. Each speaker or lecturer, apart from a few exceptions, most of them have been requested to give 3 lectures. The first 2 lectures will cover basic material, the particular area in which they're experts and which they're going to be talking about in their lectures. And the third lecture may contain, depends on the lecturer, contain some research level topics, more recent topics that they're working on. And then I should emphasize that at the end of the day, the last hour and a half of every day, there will be basically a tutorial session, which I think is very important, where the students are requested to basically, all the speakers that have given talks earlier in the day, they will be present in the tutorial session. The students can basically ask any question that they may have about the material that has been covered in these earlier lectures. Of course, I mean, they are also welcome and in particular urged to ask questions during the talks themselves. So I guess this is pretty much what I wanted to say as an introduction to this school. I am supposed to give the first lecture. This is not going to be actually a lecture related to the the main sense that some of the lecturers who will be talking later on, they asked us to provide some background information to students on some of the things that will be discussed in more detail, or will be taken as basically prerequisite to some of the things that we'll be discussing in their own lectures. So these 2 lectures, myself and also Professor Srikanth Sastry, he will give 2 lectures in the next week, will be basically not so much, any one of the things that I just talked about, but it will deal with some basic statistical mechanics questions and basically textbook material that will be required for sort of understanding or following some of the lectures that will come later on. So today and tomorrow, I am supposed to give again this is sort of background lecture on some methods that are used in studying the statistical mechanics of interacting classical systems. Srikanth will talk about some basic material on glassy systems in the next week, 2 lectures. So I'm going to then start with my lecture today, which will cover basically this thing called cluster expansion that one uses to work out the statistical mechanics of a system of particles where there are interactions, how to take into account the effects of interactions. These are the things that I'll cover in this lecture today, and also tomorrow also, 9 o'clock, 9:30. I'm going to give a lecture that will deal with liquids. Today I'm going to talk about non-ideal gases and cluster expansion, which later on, especially in the next week, when one talks about classes and things like that, will be useful to sort of understand what the speakers will discuss. And since this is basically textbook material, actually I'm teaching a course on statistical mechanics here, not a full course, but some lectures I'm giving, where I'm basically talking about the same thing. So what I'm going to talk about today is material that is available in many standard textbooks in condensed matter statistical physics. Of course, I mean, depending on your background, you probably have seen some of this stuff. There may be a few, or maybe some, who have not really gone through this material. And as I said, this material is going to be useful for understanding some of the things that will be discussed next week in the context of liquids and gases. So that's the purpose of my lecture today. How many of you actually have seen this treatment of, let's say, interactions in an approximate way in a non-ideal classical gas? Meyer cluster expansion or virial expansion, which eventually leads to something called van der Waals theory. How many of you have seen this earlier? Okay, so I was not sure about whether this is going to be useful at all, but it seems that there are a substantial number of people who have not. I'm sure you have seen it. I mean, although you're not raising your arm, you have seen a version of it. But I guess it is useful to actually go through some of the things in a little detail and try to sort of figure out what is going on in this case. So I'll be using the blackboards, and please tell me if what I'm writing is not visible from the last row of the auditorium. So, okay, so the topic is going to be a system of particles, and we'll treat the particles classically. They have some interactions, and the interactions will be specified in terms of some simple models. And then what one wants to understand is that how one takes into account these interparticle interactions in the statistical mechanics of the system of particles. Of course, I mean, the specific sort of physical systems to which this kind of treatment applies, many systems. I mean, you look at gases, and all of you are familiar with ideal gas, where one basically ignores the effects of interactions. And that's the sort of zeroth level theory. But of course, there are interactions. And so even in a gas, if the density is not very low, or if the temperature is not very high, then one begins to see some effects of these interactions. In particular, if one looks at the equation of state, which relates pressure, volume, temperature, for example, in the canonical ensemble, then one begins to see corrections to the ideal gas equation of state, even at room temperatures, ordinary gas air, for example. If one does experiments, one sees that there are some corrections. And these corrections basically come from interactions. So the statistical mechanics, what one would like to understand is how one begins to take into account the effects of interactions in a systematic way. So, of course, the effects of interactions, as I said, if you look at ordinary gas at room temperature, the effects are weak, but one has basically something which is called non-ideal gas, where some effects of interactions are present in the properties. As one goes to high densities or one goes to low temperatures, of course, most gases will liquefy. And so the liquid state, the effects of interactions become much more pronounced. The interparticle distance is much smaller, so the interaction effects becomes much more pronounced, and it's absolutely essential to take into account the effects of interactions if you want to understand the properties of liquids. And then, of course, still lower temperatures, one would have crystallization and solidification, glasses and things like that. So as one goes to lower temperatures, as one goes to more and more dense systems, the effects of interactions become more and more important. So to sort of take into account these effects systematically, what I'll do is I'll start with discussion of non-ideal gas, Virial expansion, and Van der Waals theory, to give you sort of a glimpse of how one sort of perturbative, how one can take into account the effects of interactions in a perturbative way. And we'll define appropriate small parameter, do an expansion in that parameter, and see how that leads to some results that begin to describe the physically observed properties of real gases. Then, depending on how much time that takes, today or tomorrow, I'll discuss a few things related to the theory of liquids. And then, if time permits, then at the end of tomorrow's lecture, I'll try to discuss some things about density functional theory, classical density functional theory, which is used to understand the liquid to crystalline solid or liquid to glass transition, still lower temperatures, higher densities, and so on. We'll see how far we go. So basically, first topic today is going to be clustered expansion for what is known as non-ideal gas. This is visible from the back? Barely visible, so a little bigger. Okay, so the problem is, of course, a very simple one. Is dealing with a system of particles, and we'll talk about identical particles, but classical. So in some sense, we can label these particles, and then this set of particles will have a kinetic energy in the Hamiltonian, and then they will have also, of course, effects of interactions, potential energy, which is the interparticle interaction. So we'll start with basically Hamiltonian. I goes from 1 to n. Let's say we start in the canonical ensemble, where the external variables that you fix are the number of particles, the volume of the system, and the temperature, kinetic energy, and then there will be a potential energy term, which of course depends on which kind of systems looking at. This R1 up to Rn are the coordinates. We'll be talking about three-dimensional system. So this R1 up to Rn are basically the coordinates that specify the positions of this n particles. And this is the kinetic energy term. So given this Hamiltonian, then statistical mechanics, equilibrium statistical mechanics tells you about how to proceed to understand the macroscopic properties, thermodynamic properties of a system like this. One way, if you are dealing with, if you are treating the system in canonical ensemble, is to calculate something which is called a partition function. From that, you calculate appropriate free energy, Helmholtz free energy. From that, you can calculate various other thermodynamic quantities like pressure, etc., and get an equation of state. So this is going to be the procedure, but the point is we are going to take into account the effects of this potential, and we'll sort of assume some simple model for the potential. we'll assume that the potential energy consists of a sum of pairwise interactions. And each pairwise interaction also is assumed to be somewhat simple. We're looking at point-like particles, and so the interaction energy basically depends on the separation between particle I and particle j. So we'll assume some kind of a form which looks like this. Each pair is considered once, and then you have some potential function which depends on the distance between ith and jth particle. And at this point, I'm not going to specify what this form of this V is. Typically, we'll assume that this V has a part which is strongly repulsive at short distances. If the distance between the two particles are less than some, let's say, approximate Hertz sphere diameter, then we have a very large positive potential energy. And we'll also assume that as one increases the distance, then there will be some kind of a weak attractive tail to this interaction. In particular, if I want to write down or draw some kind of a picture of how this V of R looks like, V is just a function of the distance between two particles, just a function of this variable as a function of R. There will be large positive value at short distances, and then one would have some kind of a, this is 0. So there are these two parameters, so to speak, which are important in specifying this potential. One is basically the energy parameter, and the other is basically the range parameter. So there is a distance here, which is sigma, and this bottom of the potential well has some value, which is epsilon. So these are the two parameters that one uses to specify this potential. And of course, depending on the model that we are looking at, this functional form will be given to you. So this is basically the problem. This is actually the problem that is in some sense, whenever you're doing equilibrium statistical mechanics of a system of particles, then this is the specification of the problem. You are talking about liquids or solids or gases. One has to deal with this kind of a problem where there is a Hamiltonian, which has, of course, kinetic energy term is simple, but then there is a potential energy, which basically, in some sense, is the difficult part. I mean, this is the part that one cannot take into account exactly in many, all physical systems. And so one has to sort of develop various approximate ways of dealing with these effects of interactions. So all of you are familiar with this general problem, right? So the question is then, if I ignore this term, then you have this ideal gas, and everybody knows how to deal with it. So now the question is how the properties begin to change, or how one begins to take into account the effects of these interaction terms to understand how the properties change as we go away from this ideal gas limit. Now, what I'm going to talk about today, this cluster expansion, is something, is an example of what is known as perturbation expansion. Perturbation expansion, again, the idea is again quite simple. Again, we have seen it in many different contexts. The idea is that you identify something, some parameter, some dimensionless quantity, which is small compared to 1, in the range that you are interested in. And then you do your calculation to order by order, where you take into account the first power of this small quantity, second power, etc., etc. And then if this quantity actually is a small quantity, then you can sort of conclude that you can improve the accuracy of your result by going to higher and higher orders. If you stop at the second order, then we'll get some results which will have some degree of accuracy. If you go to third order, then we'll get results in general which are better, more accurate. So the first thing that one wants to do, given a problem like this, is to identify an appropriate small parameter that one can use as in a perturbation expansion. Now, one small parameter, so what we are going to calculate? We are going to eventually calculate here, let's say if we are doing in canonical ensemble, Z, N, V, T. This is the partition function, canonical partition function. Classical systems, you put in this h to the 3n, 1 over n factorial, to take into account the fact that you are dealing with identical particles that comes here, and this is basically breaking up your phase space into little volumes so that you sort of approximately obey the uncertainty relation. And then you have to basically do an integration over the phase space variables. Product over I the pi, I goes from 1 to n, e to the minus beta, sum over I. This is the kinetic energy part, and then you have to do this integration over all the coordinate variables. And we call it u. This is the problem. So this is what you have to calculate theoretically, and then from that, taking a log of that, you get the free energy, and then taking derivatives to get other thermodynamic quantities and so on. Now, of course, all of you know how to deal with the kinetic energy term. It's a Gaussian integral that everybody knows how to do. This is what you do when you're dealing with ideal gas, for which you assume that this potential energy is equal to 0. So now the question is then how one begins to take into account this. And beta, of course, is 1 over t. And doing the momentum part, one gets basically 1 over n factorial, 1 over this thermal wavelength to the power 3n, and then you have the so, of course, in ideal gas, only this part is there, and then everything is easy and exactly solvable. This is the quantity that we are supposed to now try to evaluate, and this lambda, of course, is something that So what I'm going to talk about is basically how to approximately at least evaluate this integral that involves the interaction energy, the potential energy. Now, of course, I mean, you know that the ideal gas theory is valid, let's say, at high temperatures. So T is large, so beta is small. And so one can think that if one is basically looking for a small parameter, then one of the small parameter, the appropriate small parameter could be this beta is appearing here. U has all this pair potentials. So the question is e to the minus beta times u, whether that can be used as a small parameter. Typically, one has other problems that you may be familiar with, spin problems and so on. One has a high temperature expansion, where again this 1 over kBt is multiplied by some energy quantity, some interaction quantity, is taken to be a small parameter. But here, that doesn't quite work. Because the typical potentials that we'll be looking at, let's call it individuals, this V, the interaction potential, V of R. Even if this beta is small, V of R, there could be some values of R for which this V of R can be very large. There is this hardcore kind of interaction, strong repulsive interaction that you have at short distances. So even if this temperature can be high, but this beta is small, this whole thing cannot be always thought of as a small parameter that you will use as an expansion parameter. So that is basically coming from the fact that your potential energy of interaction can be very large if the distance between the two particles is small. So we cannot do the standard high temperature expansion. But what one can do, and that is what is involved in this clustered expansion, is to define some other parameter, which one can show is going to be a small parameter if the appropriate conditions are satisfied. And that is the basis of this cluster expansion. So I will call this quantity. This is the quantity that eventually we'll have to evaluate. These prefactors one can put in later on. This, and this will call some, where you have to do this position integration, and this u is going to be given by pairwise. So what is this quantity? Pairwise, e to the minus beta times v rij. Right, I've just written this U as a sum of pairwise interactions, and Rij is the distance between particles I and j. And now here, I introduce this quantity, which I'll just define here. Fij, this definition, e to the minus beta and the argument is that these quantities are going to be small. These quantities would be appropriate quantities for, in some sense, developing a perturbation theory. If the temperature, for example, is high and the density is low, where system is still in the gas phase, but it is not quite ideal gas because the effects of interactions are being felt. So why is this quantity an appropriate quantity? So you can see that when this V is positive, if I'm looking at potential, what the distance is here, then the potential is positive. And this quantity then is going to be negative, and if Ij mod is going to be less than 1 if V is bigger than 0. And the fact that the potential becomes very, very large and positive at short distances, that doesn't affect this very much, in the sense that even if the potential goes to infinity, then this first term goes to 0, but you still have just minus 1. So this quantity is bounded as far as the values of this quantity for positive interaction is concerned. This quantity is going to be less than 1. And so this can be used as a perturbation expansion. This can be bigger than 1 when this V is negative. And if it is sufficiently large, then this quantity, its magnitude, can be substantially bigger than 1. And then this quantity, this whole thing, Fij, can become large. But that happens only when you are looking at values of V which are negative and values of temperature which are small compared to the characteristic energy scale. So if one is looking at low temperatures, at temperatures which are comparable with the depth of this potential here, then simple physics tells you system will no longer be in a gaseous state. System will begin to see the effects of interactions in a strong way. And in particular in physics, what will happen is that system will liquefy and become a liquid. So liquid to gas transition and subsequent physics that we'll be discussing later on. Today what we are concerned about is basically at temperatures which are substantially higher than this temperature at which the gas becomes a liquid. And so in that regime again, even if this V is, the Rij is such that this V is negative, the corresponding temperature will be sufficiently large so that this quantity will be smaller than 1. So what the idea is then, use this quantity as an expansion parameter. And in some sense do an expansion where you have 1 factors of F, 2 factors of F, things like that. And this expansion is supposed to be a convergent one under these conditions, where one is looking at temperatures such that if I call this thing epsilon, the depth of the potential, this is, let's say, minus epsilon. One is looking at the temperatures where this T is going to be large compared to epsilon, so that this quantity is still going to be, its magnitude is going to be less than 1. And one is going to use this Fij as a in a perturbation expansion. So everybody with me at this point? Why this quantity needs to be defined and why this quantity is a good one for basically doing a perturbation expansion, etc., etc. And then the next is, the rest is basically technicalities. How one basically represents the various terms that occur in the perturbation expansion. They're represented in terms of diagrams, and the diagrams then break up into clusters, and that's where the word cluster expansion comes from. So the remaining part will be then basically how one then tries to evaluate this. Of course, it cannot be done exactly, but it can be done in perturbation expansion, where terms that appear later or with higher powers are going to be less important compared to the initial terms with small power. So what is this? This quantity is again integral over all positions. E to the minus beta v, I'm going to write as 1 plus f. So it's this is every pair is considered once, and then you have 1 plus this quantity that I have just defined here. So it is all of this. And the perturbation expansion basically corresponds to writing out the various terms that you get when you expand out this product. So and there are a huge number of such terms that you will get if I expand out this product. Each term, one can take either 1 or this Fij. And then, you have a certain number of Fijs, certain number of 1s, etc., etc. And then those are the various terms that will generate when you expand this thing out. So to keep track of this expansion and try to sort of see what kind of terms are necessary, at least to describe the physics even, approximately, one represents the terms that occur here in terms of what is known as diagrams. And the use of diagrams in representing different terms in a perturbation expansion is again very common in physics. Again, some of you may have seen, for example, field theory or quantum many-body theory use Feynman diagrams. Again, that's basically a way of keeping track of the various terms that you generate in a perturbation expansion. Same thing appears here. So how to sort of translate each term into a diagram? So this is what I'm going to do here. You just draw the n particles and so you draw these n dots. Each dot is representing one particle. So this, and then let's say we start with by leveling this 1, 2, 3, 4, 5, and goes up to n. So this is n minus 1, this is n minus 2, etc., etc., and some other things in between. Now, when you expand out this product, then you can take one. Let's say you look at a particular pair, I equals 5 and j equals 7 or something like that. For that, you can either take 1 or you can take the corresponding f. And every time you take this f, you basically draw a line connecting the corresponding I and j. So that way, I mean, every term in the expansion of this quantity will be represented by a unique diagram, where for the pairs for which you take 1, you do nothing. For the pairs, and if you take this quantity Fij, then in this given this n dots, you draw a line which connects the corresponding I and j. So, I mean, in general, you will get basically how many such diagrams will be there? I mean, any idea? For each term, you can take either this or that. So the factor of 2 for each term. How many terms are there? This number of pairs. N times n minus 1 divided by 2. So the number of diagrams is 2 raised to the power n times n minus 1 divided by 2. It's a huge number because we'll be dealing with thermodynamic limit where the number of particles is very large. So, I mean, instead of trying to sort of enumerate all the terms that you generate, which is of course impossible, you want to sort of develop some kind of a diagrammatic language in which all the terms that will appear here can be represented as simple diagrams. So in this case, let's say I have a diagram that looks like this. As I said, the basic idea is to connect. Every time you take this quantity Fij, you draw a line which connects the points here which represent I and j. So this diagram will correspond to a term where you have this F12. Here 3 and 4 are connected. 4 and 5 are connected. 3 and 5 are connected. And there some things will happen in between. And here nothing will happen, nothing will here. For this n minus 2, you are taking the term 1. For anything that pairs with this n minus 2, you are taking the term 1. And here you will have f. So this is a typical term that we'll get when you expand this thing out. And this is one way of representing this term in terms of diagrams where the particle labels correspond to these little circles that I have drawn, dots, and Fij correspond to a particular pair that corresponds to a line which joins the I and j that correspond to that particular pair. You can see that each pair will appear only once. That is one of the sort of advantages of using this. But a particular label here can have many Fijs associated with that. So a particular here, for example, this particular dot, there are several lines that are connected to that. So the question is then basically we are representing these terms by these diagrams, and then of course we have to do this integral, which is the evaluation, the contribution particular diagram. That's one thing, and the other thing that we have to do to sort of complete the description is to calculate the multiplicity of a particular diagram. How many times a particular diagram appears in that expansion. And then there's a contribution coming from that diagram. So if you have both of them, then we can actually at least formally write the result that you get when you do this integration. So first we try to understand what happens, I mean, what would you get when you try to do this integral? And that's fairly simple. To do that, basically, what one has to realize is that a particular diagram can be broken up into what is known as clusters. And that is quite obvious that, yes. Formally, yes. I mean, at this point, we are not saying that beyond a certain point, the interaction goes to 0. We say that there is a particular form for this function v of r, and typically we'll be looking at situations where this v of r goes to 0 when r becomes large, but that is a model-specific thing. At this point, we are not specifying, saying that if r becomes bigger than some 5 sigma or something like that, the interaction goes to 0. The full interaction has to be taken, yes. So this is what I mentioned, no? I mean, what is Fij? Fij is right. So this Fij, if this v is positive, then this quantity is less than 1. Exponential of minus something positive is less than 1. So then f is negative. Its magnitude is less than 1. So it was written somewhere. One has a little bit of a problem when this v becomes negative. V, as you can see in this picture, there are some values of r for which this v is negative. And so if v is negative and beta is sufficiently large, its temperature is sufficiently low, then this is exponential of some large positive quantity. And that can be bigger than 1. So this expansion, this Fij will be a good thing to use your expansion only when your temperature is not that low. So beta times this epsilon has to be less than 1. And then although this quantity is positive, its magnitude will be small, and so when you subtract it out, then again you will get something which is small quantity. So there is this expansion is not going to be a convergent expansion for all values of the temperature or density and things like that. Only in a limited region where these conditions are satisfied, one has a convergent expansion and then one gets physical results. But if one tries to use this expansion, perturbation expansion in regions where this kind of a argument is not valid, then one would see that there are instabilities and things like that that show up, and expansion doesn't, perturbation expansion doesn't work anymore. Okay, any other question? Okay, so as I said, the rest is technicality. So, but it's useful to go through it at least in one or two cases, so that one is familiar with how things are done in practice. So this is the terms are being represented by diagrams. A diagram consists of clusters. Each cluster basically, the definition is clear, that if you have a set of dots which are connected to each other by these lines, then you have a cluster. So here you have one cluster here, one cluster there. This also I'll call a cluster, in the sense that a cluster consisting of one side. And then this is a cluster consisting of two sides, depending on how many lines appear there. There will be clusters in between. So basically, we'll call L clusters. L cluster is basically a cluster consisting of L of these sites or dots. So this is a 2 cluster, this is a 3 cluster, this is a 1 cluster, 2 cluster, etc. And as you can see, one can do this integration separately for each cluster. Because if I look at this cluster, it contains R1 and R2. There is no other term here which will involve either R1 and R2. So I can do the integral separately for here, separately for there, like that. So basically, the integral then breaks up into a product of terms. Each term corresponds to a particular cluster. So a particular diagram, I will say, is characterized by these numbers, n sub L. And L goes from 1 to n. And this n sub L is the number of L clusters. So each diagram will have a certain number of clusters, and these numbers will be specified by this integers. NL can be 0, goes to high values, depends on which cluster, which diagram you are looking at. And this basically, this set of numbers, integers, will specify each particular diagram that in turn corresponds to a particular term that you get when you do the expansion. Yes? Physical significance is basically depends on which particular system you are looking at. If you are looking at, for example, simple systems like R1, then actually one can do a microscopic calculation to find out what will be the potential energy of two argon atoms which are separated by some distance. One knows that short distances, there will be this overlap of the electronic cloud, so to speak, and that gives you a strong repulsion. This is the sort of hard sphere type repulsion. So potential is large and positive for short distances. One also knows that there is this van der Waals interaction. There is induced dipole interaction at longer distances, which will lead to a value of V which is negative. If we start with something positive and then eventually long distances we want to make it negative, then of course there has to be a zero crossing. There is no particular significance to that particular value of R. Just a model parameter. If you, for example, consider a particular model like Lennard-Jones model or things like that, where the form of this V as a function of R is given to you explicitly, then of course one can calculate from that at what value of R the potential will go to 0. Okay? Yeah. Number of sites, yeah. Number of these little circles that you have in a cluster. Number of such clusters that you have in a particular diagram. Yes. Yes. This form I have chosen because, eventually, I mean, if you want to see this framework to lead to van der Waals equation, then there has to be a repulsive part, attractive part. I mean, of course, repulsive part is always there at short distances, but there could be potentials which will start from a large positive value and then will go like that, without a negative part. And such potentials will not show the liquid to gas transition. So such potentials, the thermodynamics of gases with that kind of potential will not be described by the van der Waals equation state. NL is the number of, L is the size of the cluster. Yeah. Yeah, so I mean, what I'm going to, this diagram corresponds to, there is a 2 cluster here, there is a 2 cluster there. So there will be N2 is equal to, assuming that here, in between you have just only no clusters, only one-side clusters. So I have 2 here, 2 there. So N2 is the number of 2 clusters. That is equal to 2. N3 is the number of 3 clusters, is equal to 1. And I have to also say N1. Now here, if I just count how many of them are there. So 1, 2, 3, 4, 5, 6, 7 are already taken into account. So N1 has to be N minus. Okay? Clear to everybody? This is basically doing 2 levels of sort of translation. This is being represented, each term in this expansion is being represented by a diagram. Diagram is specified by given these numbers, n sub L, tells us about how many L-site clusters are there in that particular diagram. There is so this NLs, of course, can be 0, can be some large integer, but there is a constraint in the sense that, of course, just as I was counting here, total number of such dots has to be equal to n. So the constraint is that sum over L, L times NL has to be equal to. So this is obvious, right? I mean, NL is the number of L clusters. So L times NL is the number of sites with L clusters, and they are summing over all L. L goes from, of course, 1 to principal. This has to be equal to n. So basically what we have to now work out is, once I specify these numbers in sub L, then what do we get from this integral? Each term in the integral, of course, corresponds to a particular diagram, and the diagrams are being specified in terms of these quantities n sub L. So basically one has to calculate the contribution coming from those terms which are represented by this particular diagram. And then also the second thing that we have to calculate is how many such terms we'll get in this expansion which correspond to a particular set of values of n sub L. So these are the two things that we need to calculate to evaluate that quantity. So first thing is the integral. So I'll define this quantity BL is the contribution from a L cluster. And a few small clusters, one can write it down quite easily. So if I look at L equals 1, L equals 1 just corresponds to a single site. So basically, B1 is the integral of dR1, let's say. And there is no factor of f. So I mean, what I'm looking at is basically looking at this. We're taking a term here where 1 is taken for every pair, and this is just equal to total volume. If I want to look at B2, B2 is something which is coming from this kind of a cluster. So let's just do the corresponding and then e to the minus beta V R12 minus 1. We have to integrate out over the coordinates of the 2 sites which belong to a 2 cluster. And it's basically, I've written out this F12 explicitly. And this integral, of course, will depend on what particular form one has for this V. Yep. Yeah, that's a possibility, yeah. And everything else is 0. So there is a possibility where n1 is equal to n, nl, l bigger than 1, equal to 0. And that satisfies that. Each diagram, because there are some n sites, you have to add up the number of sites coming from different sizes of clusters. So again, I'm not going to do this integral because I've not even given you this particular form of this V. But one thing that is important here is that V depends on the distance between R1 and R2. So I can always choose R1, let's say, to be at the origin. And the R1 integration will give you a factor of V. And then there is another integration, which is integration over the variable that tells us about the distance between R1 and R2. So this I can write as V integral dr e to the minus beta of V of R minus 1. And similarly, if I want to write down the contribution from here, I will have, let's say, this F, as I've written down here, F34, F45, and F35. But again, all of these terms depend only on the separation between these two. This is something that we have assumed, that the potential depends on the distance between particle 1 and particle 2, particle I and particle j. So in all of these integrations, I can actually take one of the coordinates at the origin and then do an integral over the relative coordinates. So each of these, B1, B2, B3, etc., all of them will contain a factor of volume, and then there will be some integral which you'll have to do. So that is something that you have to remember. Also, there is another thing that you have to remember is that if I specify L, then it does not uniquely specify the cluster. As I go to large values of L bigger than 2, then there are different clusters which will have the same value of L, but the corresponding integral will be different. So is that obvious to everybody? Because here I am looking at a 3 cluster where you have 3 factors of F. But if I had removed this, that would still be a 3 cluster, but there will be 2 factors of F. So the corresponding integral will be different. So you have to keep track of the fact that at a particular value of L, you just don't get just one type of cluster, but several clusters. As you go to larger values of L, it becomes actually quite difficult to enumerate all sort of topologically distinct clusters that you have for that particular value of L. So you have to take into account, but once you have drawn the particular cluster, then from that you can calculate what the integral is going to give. Okay? Yeah. So then, the anisotropy will then come in the integral. So when you are doing this dr integral, you cannot just write it as 4 pi r squared dr, but you have to do it x, y, and z integrals separately, which will take into account this anisotropy. Okay, so this factor is something that one can do. But as you can see here, at the level of L equals 2 or even at the level of L equals 3, one can do these integrals. Yeah. Yes. Yeah. No. All possible clusters have to be taken into account. If you are looking at 3, 4, and 5, then you can have a situation where you have this, what I have written down here, F3, 4, F4, 5. You can have a situation where you have F3, this one, F4, 5, F5, 3. So there are 3 different ways in which you can have a 3 cluster which will have 2 such lines. There's combinatorial problems, combinatorial factors that you have to work out. But there will be also one which I had written out at the beginning, where you have all 3 of them. Each of these correspond to different factors of this F, which I and J are connected by a particular line to look at, and that will give you the F. So you can ask, now we have this 3 clusters of 2 different types, where everything is connected and where we have only 2 lines. Which one actually will give you a bigger contribution? That is a valid question. That given, let's say, high temperatures and low density, whether one needs to take into account both of these kinds of clusters, or one cluster contribution is going to be small compared to the other. And there, this fact that these Fs are the parameters that we are using to order your perturbation theory, that becomes important. Something that has 3 Fs is going to be less compared to something that has 2 Fs. So if I look at the 3 cluster, there will be these 2 different types, and one type, its contribution is going to be small compared to the contribution coming from the other type, if these conditions are satisfied, that the temperature is high and number density is low, etc. Okay? So I'm going through this in a little detail because later on you will see that in second week of the lecture, for example, there will be a set of talks where one actually looks at this series for hard spheres, and then goes to higher dimensions and so on and so forth. There's all sorts of technical things, but basic is this, that here you are doing this expansion as a perturbation expansion, which takes into account the effects of interactions. So this is the integral. As I said, there is integral, but there is also a combinatorial factor, counting factor, which is basically now I look at a situation where I don't specify these labels. I have n such dots, and I have connected them in some way, and then I get a diagram which is specified in terms of these numbers. The question is how many ways in which I can put these numbers, which will give you this diagram. So, I mean, I have written down one here, there's 1, 2, etc., 3, 4, 5, etc. But a permutation of these n labels also corresponds to the same diagram when we are saying that the diagram is specified in terms of these n sub l's. Right? So basically then the counting factor is how many different such diagrams will appear when you do this expansion completely. And so what we have to do is then we have to first of all calculate the contribution coming from the integral, and then multiply it by how many times this particular diagram is going to appear, and then sum over all possible diagrams. That's going to be the final result of this quantity that we want to calculate. So the counting factor. So when I specify a diagram by this n sub l's, and then I want to find out how many different ways I can assign indices to this n points or n dots that I have in that particular diagram. So the counting factor, or combinatorial factor, again, you know, the arguments, I mean, it would be instructive for you to actually look at small values of n and then see how these counting factors actually arise. But the arguments also are quite simple. Basically, you'd say that if I have this n indices to be assigned, there are n factorial ways of assigning these indices. So first case would be, the counting factor would be n factorial. But this has to be corrected, because permuting the labels inside a particular cluster does not give you a new term there. If I look at F12 or F21, that is the same. Similarly, if I have something that looks like this, and that, again, you know, if I say, if I permute the labels 3, 4, and 5, then doesn't give you a new term in the expansion. So permuting the labels that occurred inside a particular cluster, that doesn't give you a new term. So one has to make a correction for that. And that correction is permuting the labels of a L cluster give you L factorial. And if there are n sub L such thing, this quantity gives you the correction factor associated with saying that if you permute the labels inside a particular cluster, L cluster, then that doesn't generate a new term in the expansion. And so L factorial, so many of them are there. And then there is other thing is when you have permuting the labels between 2 L clusters. So here, we are looking at here and there. And if you permute the labels associated with this, with that, again, you get the same term in the expansion. It doesn't generate a new term. So there will be a product over L, n sub L. So this is just looking at all permutations, but then we have to look at the situation where some permutations do not generate a new term that you have in the expansion. And there are two sources of that. One is coming from here, where you are looking at permutations of the labels that belong to a particular L cluster. And then there is a term coming from here, where you are permuting the labels associated with two different L clusters. So this is the number of times a diagram which is specified by this integers n sub L is going to appear. And you can calculate the contribution from such a diagram by doing these kind of integrals. So your basic result eventually is going to be a sum where you're summing over all values of n sub L modulo the constraint that L times ml, sum over L has to be equal to n. And then you take this term multiplied by that number and sum over all possible values of nl. So the quantity that I had started out to evaluate, this S sub L, is going to be written then in the following way. And then there's a prime. Prime basically means that, so each NL, of course, can go from 0 to something, large value up to n. But this sum is equal to n. So this is, you cannot sum over all the NL values independently. And this prime basically represents that constraint. And then you have the number, which is n factorial, product over L. DL I have defined to be as a contribution from L cluster. N sub L is the number of such clusters that are there in your diagram. So you have to raise this BL to the power NL and then take a product of all possible Ls. So this is basically the final result written in terms of now these quantities. These are the quantities that I have to evaluate. This B1, B2, B3, etc., etc. Of course, as you can see here, as I go to large values of L, the evaluation of these cluster integrals become more and more difficult. So in practice, actually, one will not keep very high order terms, except in special cases, which will be discussed in the next week by people who are looking at the art sphere problem. And so then the question is, first of all, I mean, what this sum gives me, and then what do I get if I keep only a few terms in this expansion, and to what extent that describes the physics. So now there is a product over all L, and then there is this sum over this integers n sub L. But the sums become, you cannot do the sums independently for different L because of this constraint, that sum over this constraint. So it is useful, and actually the way the calculation goes is to basically go to the grand canonical ensemble. So far we have been talking about the canonical ensemble, where you keep the number of particles fixed. But in the grand canonical ensemble, you of course allow the number of particles n to vary. And then there is a weight factor, which takes into account involving the chemical potential, which basically limits the fluctuations in the value of n that we are going to have eventually. And in the large system size limit, thermodynamic limit, where n goes to infinity, the results that you get from the grand canonical ensemble are supposed to be the same as those you will get from the canonical ensemble, equivalence of ensembles. So to remove this problem of this constraint, we'll now go to the grand canonical ensemble. So here, the grand canonical partition functions, and it will now be a function of mu, and then v and t. Earlier we had nvt, but now we are having a chemical potential. And this is defined to be sum over n goes from 0 to infinity. e to the n times beta mu, and the canonical partition function. So ZNVT I had already defined there. And it is defined apart from these prefactors, lambda to the 3n and n factorial and so on and so forth. One has this quantity, that is the integral over the positions, that is the difficult part. And so one has to then plug that in here. Expression for this S of n that one is getting here, one would have to plug that in back there. And then the sum over this n sub l's become independent, because now the constraint that the number of particles has to be fixed is no longer there. I choose arbitrary values of this n sub l's that will give you a particular value of n, but as long as I put in the corresponding weight factor associated with that particular value of n, and then that term is already there in this expansion, and so one can do the sums over n sub l's independently, and you can see that this sum over n sub l will have this term, something raised to the power nl here, something raised to the power nl there, and then you have a 1 over nl factorial downstairs. So x to the n 1 over n factorial, and when you sum over n, that just gives you an exponential function. So each nl sum will give you an exponential function, and then you have to take a product over all l going from L, of course, goes from L equals 1 to infinity now, because there is no constraint on capital N anymore. So I will not write down the intermediate terms that are quite easy to do. What one has to do is, here there is an N here, so this I has to write as sum over L times NL. So then everything is written in terms of this L's and LL's, and since there is no restriction like this anymore, one can sum over the NLs independently for each L, and each one gives you an exponential factor because of this factor that you have 1 over NL factorial. Just here, n sub L factorial x to the power NL. Here we have something that raised to the power NL, something raised to the power NL. Here also you have something raised to the power NL. So all these things combine into this x, and you basically have this becomes product over L exponential So this is quite neat in the sense that, you can actually summing all such diagrams and eventually getting something which has a fairly simple expression. There is again, L of course goes from, now n goes from 0 to infinity. So the size of a cluster can be 1, could be arbitrarily large. And then you have this quantity to the beta mu as an expansion parameter. We'll call that Z, which is called the fugacity. So what we are then is going to do is now fairly routine, that once you have the ground canonical partition function, take the log of that, multiply it by minus kBt to get the corresponding free energy. If you differentiate it with respect to volume, then you will get the pressure. If you differentiate it with respect to the chemical potential, then you will get the average number of particles. So then one can write down what the equation of state is going to be in terms of these quantities. The quantities that are there that are to be evaluated, again, as I'm emphasized, are these quantities. The integrals associated 2 clusters, 3 clusters, 4 clusters, like that. Okay, so if this is clear, then what time do we have? 20 minutes, yeah. So I can write down various consequences of this, but the whole procedure should be clear to you, that how one is actually doing the perturbation expansion and representing them by diagrams, and eventually summing all diagrams to get a result, which now can be written in terms of these cluster integrals. Yep. Yes. Yeah, so there will be a V3, which will have a contribution coming from the situation where all three are connected. There will be also a contribution coming from where they are connected in pairs. But in pairs, there are three different ways in which you can do it. So that factor of 3 has to be included. So this B3 will be, if I want to write it in diagrammatically, B3 will be 3 times this diagram plus so this multiplicity factors, etc., combinatorial factors, those are important and you have to keep track of that. But as I was saying, you see this contains 3 Fs, whereas this contains 2 Fs. So if you are in the region where this F is a small parameter, then one of them is going to be more important compared to the other. But both these are taken into account when one is calculating third virial coefficient. I'm just going to define that and then we'll see. So also one makes this, then one looks at the grand canonical free energy, Ln. And then this product over L becomes a sum over L. E to the beta mu divided by lambda cubed, whole thing raised to the power L, BL divided by L factorial. A few things, the rest is basically now taking derivatives of this with respect to various parameters, which basically phi is a function of, again, mu and v and t. So you have to take derivatives. One thing that you have to go back and remember is that if I am looking at these BLs, each of them contain a factor of volume. Why does it contain a factor of volume? Because you are integrating over all possible values of R, R1, R2, R3, etc. But the integrand depends only on R1 minus R2, R2 minus R3, etc., etc. So one integral will always give you, is free, and that will give you a factor of V. So if you wonder, here, where this V is coming from, this V is coming from this V sub L. And to make notation a little simpler, I will write this quantity BL as L factorial. Then there is a factor of volume. Lambda is to the power 3L minus 3. BL tilde. These are defined then in terms of these BLs. And the factors that I have put here are quite obvious why I'm putting it here. This L factorial goes with this L factorial there. Lambda to the 3L goes with lambda to the 3L over there. This lambda to the minus 3 is simply to make it dimensionless. This V over lambda cubed eventually when we, and this Z is a fugacity. So this phi is written as minus KBT. Is a V. Is a V over lambda cubed, then this BL tilde, and then Z to the L is basically this quantity, Z to the L. So this is an expansion now in terms of this fugacity, and this expansion is called the Mayer expansion. What we'll do now is basically use this to calculate the equation of state and express the equation of state, pressure as a function of volume and number density, and that expansion is a derived expansion from here. This is called the cluster expansion. And if I truncate that expansion at very low order, the lowest non-trivial order, then one gets from that the van der Waals equation of state. So a few lines of algebra. N bar minus partial derivative of phi with respect to mu. And mu comes in here, Z is equal to the beta mu. So this is nothing but sum over L, V divided by lambda cubed, L BL tilde, Z to the power L. And the pressure equation is obtained by derivative of phi with respect to the volume. The volume is explicitly there. So the pressure equation is kBT one over lambda cubed z raised to the power L BL tilde. So this is the equation of state, and if you can calculate now, you see that the sums are all sum over L goes from 1 to infinity. Yes. Mu negative. Classically, we will take mu to be negative, yes. So this Z is a small parameter, and you are expanding in this small parameter. The expansion you can write down if you know how to evaluate this, these integrals, cluster integrals for arbitrarily large values of L. So that, of course, is not possible. I mean, you know, as you can see here, the integrals become more and more difficult as one goes to larger and larger values of L. So the question is, I mean, if my partition expansion is useful only if I stop at some small value of L and expect that the results that I'm going to get from there are going to be physical. So that is what, fortunately, is the case here. Under certain circumstances, as one is very far away from the gas to liquid transition, one is at high temperature and low density, then this perturbation expansion is a convergent one, and one gets reasonably good results simply by keeping the lowest order terms in the expansion. So from here, I mean, one would do two things. As usual, grand canonical ensemble, you have average number of particles. So if I want to make a connection with the canonical ensemble, then I set that equal to n, the actual number of particles. Then use this expansion to determine z in terms of n divided by v. So, I mean, I take this v on the other side. This is number density, is again written as expansion in z to the n powers of z. So I can sort of invert that and write z as a power series in n. So, and then substitute that here. So then you will get the pressure as a function of number density. Pressure as a series, infinite series, involving again coefficients, and those coefficients are called the virial coefficients. So eventually you will get using capital P, K Boltzmann T will be written as sum over L goes from 1 to infinity, capital B sub L, little n raised to the power L. So, and of course, I mean, this is the expansion I like better, because in some sense, you know, the quantity that we're expanding in is a dimensionless quantity. The z is e to the beta mu, and it's, of course, a number. Whereas here, you are expanding in terms of this little n, which is not a dimensionless quantity, but you can cast this in the form of n divided by lambda cubed, this lambda being another length scale that you have in the problem. But this is the historical thing, and these BLs are called virial coefficients. And to calculate this BL, what you have to do is, first of all, you have to write these BLs in terms of these quantities. And this is done, as I said, by writing this Z, the fugacity in terms of little n from this equation, and then substitute that here. So then this BLs will be written in terms of this BL tildes. BL tildes are written in terms of this BLs, original BLs. The BLs are calculated from those integrals. So that is the description. Given a potential, in principle, one can calculate what this U1, B2, B3, etc. are there. As you have guessed, this B1 is just simply equal to 1. And that gives you the ideal gas equation of state. P divided by KBT is number density. That's the ideal gas equation of state. If you want to look at any correction to the ideal gas equation of state coming from these interactions, the first term is B1, virial coefficient, and this B1 involves this integral. And this integral, of course, again depends on the form of this little v that we're going to have. We'll assume that this V is generically of that particular form, that there is a length scale sigma such that for R less than sigma, the potential is very large and positive, and for R bigger than sigma, the potential is negative, but small. And we are looking at temperatures where kBt is large compared to the depth of that potential. So then one can calculate this B2. And this is an exercise that if you want to sort of do this very simply, that you should do, that given a particular form, in particular, if we assume that this V of R goes to infinity for R less than sigma, and then V of R is negative for R bigger than sigma. But you don't have to specify the form of V of R. There will be an integral that will involve this V of R magnitude as a function, R squared dr and things like that. Then from that, and if you keep only B2, so of course, I mean, this is 1 to infinity. So first term is the ideal gas, and second term is the first correction. And the point is, if this perturbation expansion is going to be good, then under certain circumstances, just by keeping the first non-trivial term in the perturbation expansion, one should get equation of state, which is reasonable. And it's an exercise that I leave for you to do. You keep only B2, and you assume this properties of this interaction potential, and then you will see that this will lead to the van der Waals equation. Equation of state, which will be this P plus A n squared 1 over n minus B. And this B will come from this part, the strongly repulsive part, which is basically the hardcore, I mean, assuming a hardcore potential, this is basically the hardcore volume multiplied by some numerical factor. And this other term, A term, is basically coming from the negative part of this potential. And in particular, it involves an integral over the magnitude of this V from sigma to infinity. And again, depending on the particular form of the potential, some number. So basically, then this shows that one can actually develop some kind of systematic perturbation expansion to take into account the effects of interactions in a classical system of particles. And the expansion is that developed in terms of these quantities, this F's, which we have argued that is a reasonably good expansion parameters in the region of parameter space where the system is supposed to behave like a gas and far away from the gas to liquid transition. And then the whole perturbation expansion can be formulated in terms of diagrams, and one can get a very nice closed form expansion for the equation of state. This is the equation of state, how the pressure depends on the number, density, and temperature. But the thing is that these coefficients, these virial coefficients, are the ones that are required to actually get the final result. And if you keep only the first, second virial coefficient, the first non-trivial term in the expansion, that gives you this well-known equation of state, van der Waals equation, which is of course determined from experiments, and then there was some sort of hand-waving arguments as to where the different terms come from. And here explicitly you can see where these different terms are coming from. One is coming from the fact that at short distances one has something like a Hart sphere kind of exclusion, and so this B basically comes from that, and then you have a weak negative part of the potential, which gives you this first correction that you have, A n squared term in the van der Waals equation. So I guess my time is more or less out. So I'll just end this by giving you, again, something that I'm sure you have seen in some form of other, in some course, that if I look at the van der Waals equation of state and then do this isotherms, P as a function of V or P as a function of N for different temperatures. At relatively high temperatures, it gives you physical results. As you go to lower and lower temperatures, then this kind of equational state line that develops certain features which are unphysical, which gives you negative compressibility and things like that, which are of course not allowed in a system which is in thermodynamic equilibrium. So then you have to understand what is going on there. And what is going on there is that we are trying to use this equation under circumstances for which it should not be used, which is basically here, if you just keep one term in the expansion, then you don't expect that that will work all the way down to temperatures where the system will become a liquid, so gas to liquid transition. So one can actually get some information about the gas to liquid transition just by looking at the van der Waals equational state and looking at its instability and then doing something which is known as Maxwell construction and things like that. So I'll not go through that because that is worked out in many standard textbooks. But then the question is, I mean, when one is entering that regime where this simple perturbative expansion is no longer valid, even if you keep higher order terms in the virial expansion, then what does it? How does one then look at or theoretically study such situations? That will take me to some discussions of liquid state theory, which is basically what I'm going to do in the next lecture, and that's pretty much it. I also wanted to talk about some density functional theory, which I don't think I'll have time for, but if there is some special interest, then we can discuss that in some tutorial or something like that. Okay, thanks for your attention. And questions.
Okay, we can have one or two quick questions. Yes.
I'm Jishnu from Brandeis University. So my question is that we do this expansion particularly for large temperatures, right? So is there a similar expansion that we can do for very low temperatures, like exclusively for low temperatures?
Oh yeah.
Something similar.
I mean, we have to basically, then your basis cannot be a gas. So here we are starting with the ideal gas, and then you are looking at the first correction to the ideal gas equational state. At very low temperatures, you don't expect the system to be gas, except for, maybe, if you're looking at helium or something like that, then even at low temperature, system doesn't liquefy. But then for those systems, quantum effects become important. So there is no sort of system that I'm aware of where the system will remain a classical gas at very low temperatures. But in most cases, what is going to happen? As you go to very low temperatures, system will first become a liquid, and then it will become a solid. So if you want to study the low temperature properties of a solid, temperature is very low. Then there are ways, there is harmonic theory. You look at phonons, crystalline solid, then you look at phonons, and treating the phonons as harmonic excitations, you can work out the low temperature properties of a crystalline solid. For amorphous solid, again, there are lots of numerical work where one looks at similar things. Question is, even for those systems, classical treatment of phonons is not a good idea. Because if you look at temperatures which are much lower than the Debye temperature, then the phonons themselves have to be treated as bosons. So at very low temperatures, first of all, your reference state changes. Instead of looking at going away from an ideal gas, you have to look at basically going away from ideal solid at rest. And then the corresponding excitations you have to take into account in a study of the thermodynamics. So there will be some discussion, I think, of harmonic excitations in amorphous systems in, I think, next week or something like that.
Any more questions? If not, we break for coffee and come back at 11:30, I think.